Okay, Assalamualaikum and salam sejahtera to all. Today we're gonna to continue our lesson in chapter 5, which is about a beam and frame. Previously we talked about trusses in chapter 4, if you still remember. Okay, kita pergi ke introduction. As I said before, perbezaan di antara trusses dan juga beam adalah jika trusses we just consider for the axial force direction. However, for the beam there are involved force for both in axial and also for a vertical direction. So you need to know how to differentiate between a beam and trusses. Okay, what is beam is actually? Beam are a slender member that are used for supporting a transverse loading, either it's vertical or axial. Okay, long horizontal member used in building, bridge, shaft, and also in automobile and also the aeroplane structure. Okay, so for in a general horizontal beam with loading is shown in figures 5.1. As you can see from here, right, this is your simple beam system. Okay, and B shows the deformation of the neutral axis. So when you can imagine that jika kita ada beam di sini fixed on the left and then they have the roller on the right. So bila kita ada external, we have the axial force and also we have vertical force acting on the beam, so we can see it will deform, right? So this is the deformations of the beam with respect to the angle theta here. Okay, so that's they are telling you here. So figures for 5.2 below shows the bending of stress distribution, right? This is your stress distribution occurred on your beam, the cross-sectional one. So they have considered for the axial load here, and also they have also for the vertical load, which is the moment, all right, acting on the beam. Okay, so from a small deformation, so we can consider that. I think you quite familiar with this formula, this equation. For the sigma, we can find by this formula, negative m over I times by y, and also for a strain is about stress over E. Okay, they have no negative here, I'm sorry about that, this is my mistake. Okay, so we continue. So from that, for double differentiations of the V, what is V? V is the deflection of the centroidal axis of the X. You can see that what is the V here is mentioned to here, right? So it's equal to m over EI, when m is the bending moment and E is the Young modulus and I is the moment of inertia. I think that is quite straightforward for you, and I think you have learned it before in a solid mechanic, if I'm not mistaken. So we go to the next section. We talk about the potential energy approach. So from here, the general form to represent the potential energy approach is represented by U is equal to half the integration to 0 to L length times by EI, the double differentiation square dx minus integration of 0L PV dx minus summation of the PV in M and also MV in K. What is P? P is a distributed load per unit length, and PM is a point load at a point M, and also MK is the moment of the couple applied at the point K. VM is the deflection at the point M, and V prime K is the slope of the point K. I think this section is just to get some overview of that. No need to remember. And also in order to find the solutions in energy approach, we promote the mathematical solution we call as a Galenkind approach in order to get the equilibrium equation acting on it. So I'm not sure from here because it will not be covered in your final, but for your information, for the total, if you use the Galenkind approach in order to get the equilibrium equations of the energy, for example, you can get it by submission of all these things is equal to 0. Okay, so you can mention here when they provide you is equal to 0 here, so that is the governing equations for the Galenkind approach, right? So in order to solve the energy approach in the system, so we continue for the next section. So how we want to formulate our finite element in a beam structure. So from that, the beam is divided into element. Okay, so from here you can see that the beam is divided into different nodes and different element, and also each node has a 2 degree of freedom. That is a basic for you, and typically the degree of freedom of node I are Q2 minus 1 and Q2I. This is similar with the previous lesson, right? If you still remember. So from here the difference is just the direction, because if you still remember, the degree of freedom for the thrust is about X and Y, right? The direction, but for the beam there has a different one because they are considered for the axial and for the vertical one. So from here, this is how they are calculated. For that, Q is 2I minus 1 and also Q2I. Okay, if you want to know that the Q2I here, the Q2I minus 1 is a transverse displacement. This is the transverse displacement, and also this is for the vertical. Okay, this is the vertical displacement, or we call as a slope or rotation. Okay, so in order to find the global displacement vector, this is how you calculate that, the transpose of the Q1, Q2 until a Qn. And then for a single element, the local degree of freedom are represented by this one. Okay, it's similar one. If you still remember from the previous lesson, when we talk about global, we need to what we call use a capital letter, right, instead of your small letter which represent of the local degree of freedom. Okay, so from here there's a special about beam, because we introduce new names we call as Hermite shape function. Okay, which is represented by H here. Okay, what is a Hermite shape function? Hermite shape function which satisfy a nodal value and slope continuity requirement is given by this one. This is the formula on that, which is Hi is equal to I is a small letter H, in the bottom one, Hi here is equal to Ai plus Bi phi plus Ci phi square plus Di phi cube. Okay, the condition given is following table must be satisfied, and this is how they are assumed, they are calculated for the Hermite shape function based on a phi is equal to -1 and also equal to 1. Okay, okay, I think we can continue. Alright, so this is what we are talking about. So from here, as we did it before, if we have our system of FEA system here, so the most important thing is how we want to construct the connectivity table. So from here, for the element 1 is connected 1, 2, element number 2 is 2, 3, and so on. Okay, so this is quite straightforward for you. The most important thing is how you need to understand how they put the number in the degree of freedom, Q1, Q2, Q3, Q4, and so on. Okay, and then when you separate it in order to solve every stiffness matrix for every element, for example from first element 1 and 2 nodes, So you can see that Q1, Q3 and Q4. Okay, and then V1 is actually talk about a Q. It's a similar thing. Okay, and then the coefficient of AI BICI can be easily obtained by opposing this condition. So in this one, this coefficient is given from here, right? AI BICI DI here is calculated from this one. Okay, and then you can consider for H1 how you want to calculate for H1, H2, H3 and so forth, and so on. So H1, H2, H3 and H4. So this is what you get from this table. Okay, when you consider phi is equal to -1 for H1, so when you substitute the phi is equal to 0 here, so you will get your H1 is equal to 1. Okay, you can try at your home and you can see how it will be calculated. Okay, we continue. Hermite shape function can be used to write a deflection. So the most important thing why we need to learn about the Hermite shape function, because we want to use it to write the deflection. We want to calculate the deflection of the beam, right? So this is the general formula that you need to understand and you need to remember. Okay, this is H1 V1 plus H2 dV over dV1 H3 V2 plus H4 dV2. Okay, okay, and then they have some derivation on that. So the coordinate transform by the relationship. So this is how they calculated for the x. So and then since if you still remember this equation is equal to x2 minus x1 divided by 2. Do you still remember? For in order to get the length, the x2 minus s1 plus y2 minus y1 square and then square root, right? So we have our the derivations of the dx over dv is equal to le over 2. Okay, and how you get this one? You just substituted it. So let me try. So from this, when you substitute, all x is equal to x1 plus x2 over 2 plus x1 minus x1 over x2 minus x1 divided by 2 phi. So when you substitute the le here into this, so it will become le over 2, right? So and then when you differentiate dx over d phi, you will get le over 2, right? This is how they are derived. Okay, so and then they use the change rule, and then in order to get the dx over dv is equal to dv over dx and dx over dv. So you can terminate the term of the dx in order to calculate for the, sorry, you will get the dv. This is the dv here for the chain rule. Yeah, sorry, this is dv. This is dv over dv is equal to dv over dx times by dx over dv. So you need to change that. Dx is equal to not dx. This is a dv. So this is how they calculated for that. Okay, and then we continue, noting that dv over dx evaluated at node 1 and 2 is q2 and q2 and q4. So the dv over dx ni di mana? Di q2 and q4. Q2 and q4 here, the vertical or the rotation one, the rotational one. Okay, we have now here. Okay, we just substitute all the formulation upstairs, and then we get the general formula from the previous one, and then we improvise it, and then we get this formula, this equation. And then you need to remember, you need to understand how you want to implement the formula for the deflection is equal to h1 q1 plus le over 2 h2 q2 plus h3 q3 plus le over 2 h4 over q4, which may be noted as, and this is the short form of these equations, right? So h times by q with respect to the all the degree of freedoms of the nodes. Okay. Oh, sorry. We continue a little bit about this one. So, and after that, when you finish, get the value for the deflection, so you can continue in order using the element strain energy that I said it before to you. So it's equal to half EI integration of the double differentiation of the V over dx square dx. This is just for your knowledge and for your for your understanding. And then in order to calculate for your element stiffness matrix, and this is important, if you still remember, for every element we need to calculate the stiffness matrix for every element in the system. So from here, this is how they calculated for that. The LE here represent the length of the beam. So this is practice when the L is equal for every system. It means that if you consider the L is equal the equal length of the beam, so you need to use this kind of formula. Okay, so now we continue for the next section. Is about the load vector. So the most important thing about the load vector is you need to understand for this, right? So if they are given to you the distributed load like this, which are connected between node 1 and node 2, and they have their own distributed moment here. So from here, how you want to calculate the what we call the axial and also for the vertical one, or we can talk we can say that how we want to calculate for the shear and also for the moment. So this is how they calculate for the load. The shear load here is P times by LE over 2, and this is similar, and this is how they calculated for the moment. Okay, it's P L square over 12, and this is positive and this will be negative. You need to remember and you need to understand that in order to answer the question in the final. Okay. Okay, this is a little bit about shear force and also for the bending moment. And I said before, I think you are quite familiar with this equation because they are covered in the solid mechanic and also a static, if I'm not mistaken. So how you want to calculate for the moment is equal to EI double differentiation for the d square V over dx square. So how you want to find the shear force equal dm over dx, and V is the deflections, right? If you still remember how you want to calculate for the deflection deformation is equal to H times Q. So this is the expansion of the equations of from the above. Okay, so this is the basic knowledge. I think you are familiar on that, how you want to calculate for direction force. Okay, now we go to the example in order to get some overview and then to get more understanding on that. Okay, the solution is we consider we go through this. Okay, the question asking you, we consider the two elements formed by a 3 nodes. Okay, go to your diagram. They have 3 nodes, 1 2 3. Understand? Determine first the slope at 2 and 3 nodes, and second one, the vertical deflection at the midpoint of the distributed load. Okay, so that's the thing that you need to find. Okay, so for the solution for the first one, I think this is similar with the previous solution that we did. So the first of all, we need to calculate for the stiffness matrix. We consider the two elements formed by a 3 nodes. Displacement Q1, Q3, Q1, Q3, Q4, Q3 and Q5 are constrained to be 0. Am I right? So let me see either it's correct or not. So it's correct. Q1, Q3, Q5 and Q1, Q2, Q3, Q1, Q2, Q3 and Q5 is fixed. Okay, it means that is 0, correct? And Q4 and Q6 need to be found. So you need to find the Q4 and Q6 here. Okay, since the length and the section are equal, so we can implement this kind of formula that I mentioned to you, the matrix formula for the stiffness matrix. How we want to know the length section are equal? From the equation. So from the questions. So this is element 1, element 2, which have a similar length. So is make our solution become easier. Okay, so from that you calculate elements of the matrix for element 1 and 2 are given. So this is the K1 and K2 because they have a similar L here, so we can use same element stiffness matrix for every element. So this is stiffness matrix for element 1 and also element 2. So element 1 is connected the degree of freedom of Q1, Q3, Q4, Q3, Q4, and for the element 2 it connected between Q3, Q4, Q5 and Q6. Okay, so this is what I'm talking about. So from here, how you want to get this kind of diagram or degree diagram, what I call the diagram here. Okay, is if you still remember, I inform you that you need to understand from this, right? So you implement all this calculation on that, and then you will get the value for the bending moment and also for the shear force acting here, right? You need to get this one. I think in the exam we not provide you this diagram, so you need to understand, you need to know how to get this diagram from this diagram. This is the normal diagram that given from the equation. So this is how you need to interpret it to get this kind of diagram, right? Okay, refer to figures. Okay, the global applied load F4 is negative 10 and 10. And negative 1000, and F4 is plus 1000, as been mentioned here, right? This is F2, this is F4, this is positive and this is negative, so it's very straightforward one. So from this case, the counterclockwise is the negative, and the clockwise is negative and counterclockwise is positive. Sorry, yeah, correct. So obtain from this. Okay, we use here the elimination approach. Using the connectivity, we obtain the global stiffness matrix from after elimination is from here. Why they just only 2 by 2? Because they just consider for the to get the Q2, a Q4 and a Q6, right? And all of that are is mentioned here because Q1, Q2, Q3 and Q5 are 0. So that's why you get 2 by 2 matrix, which is very small and very easy to solve. So from here you can get it straightforward. Your deformations or your deflection for your Q4 and your Q6 of your degree of freedom of the nodes, right? So from that, so we continue on that for element number 2. Okay, so we need to consider for the element number 2, Q1 is equal to 0. Okay, we just we just improvise it from the element 1. So for element 2, now it will become Q1, Q3, Q4, Q5, right? So that they are tell you here. So Q1 is 0, Q2 is similar with the Q4, Q3 is 0, and Q4 is equal to Q6, right? They just change that. This is the first element and this is the second element. Now we want to see at the second element in order to answer for the second question, right? So you understand this one. Again, to get the vertical deflection at the midpoint, kita kena pakai formula yang H tadi. Okay, what is H? H is the Hermite shape function, right? So from that, this is the formula that you need to use. From where? From the general formula that I discussed with you before. With this one, this is the general formula one. So you just substitute for every value of the Q1, Q3, Q3 and Q4. Okay, so from that, and then you substituted it, so you will get this thing. Okay, okay, and then you will get your deformations at the vertical deflection of the midpoint. Okay, the H6C is given from, get it from here. Okay, okay, now we solve for the simple beam. Now we want to continue how if our problem consider for how we want to solve the beam if they have more than one member. It means that they have a connected beam in one structure, or how we want to solve if the beam is not in a horizontal way, so means that they have the angle for that. So we need to understand, and we need to learn about the plane frame. Okay, so here we consider the plane structure with the rigidly connected member, and then this member will be similar to the beam except that axial load and axial deformation are present. So this is how I talk about how we want to solve this type of beam if they have some inclinations, or they have some angles acting on the beam. Okay, so we go through the formulation as usual. For each node we have a two displacement and a rotational deformation. So from here, if you can see here, they have a two displacement. They have a Q1, they have a Q2, right, and a rotational deformation. This is special about the plane frame for the beam. Okay, so they have a Q3 which represent of the rotational deformation. So now for every node you need to consider 3 degrees of freedom for every node, which is you have Q1, Q2 which is the displacement, and also you have a Q3 which is represent the rotational deformations of the nodes. Okay, so from that, the total displacement vector, the nodal displacement vector in the global system is given by Q1, Q3, Q1, Q2, Q3, and then Q4, Q5, and Q6. Okay, correct, for one element. And then the nodal displacement is similar with the previous one. So, and then is how they calculate for the local global deformation, and this is how they calculate for the transformation matrix. Okay, they are considered for the LMM. If you not remember what is LMM, go to the previous lesson how they calculate for L and how they calculate for the M is related with the length. Okay. Okay, this is how they calculated, and this is how they are considered for the stiffness matrix of the beam structure. So you need to consider for the E A over L here, and then from the element strain energy and in the Glenn-Kahn approach, we recognize the element cinematics in the global coordinate to be like this. Okay, and then from the local to be become a global. Okay, this is the local, and this is the this is local and this is the global from the equation, equation for the L transpose time by K stiffness matrix in local and times by L. Okay, if there is a distributed load on a member as shown in figures 5.7. Okay, this is 5.7. So we have this kind of calculations, this kind of formula. Alright, so this is what I'm talking to you before, similar one. So now I think that's all for a beam. We go to the last example in order to get more understanding on that. Okay, determine the displacement. The question is about determine the displacement and rotation of the joint for the portal frame shown in figures 5.8 below. So you have this structure, and then they're asking you to find the displacement and also the rotation of the joint for the portal frame. So means that they need to find the what you call the displacement and the rotation at node 1 and also the node 2. Okay, so what we need to do first is similar with the previous lesson. First we go to the connectivity table. So for element, so we have 3 elements here, 1 2 3, and then connected between for every node. So first we need to go to the element stiffness matrix, how we want to calculate that. So noting that K1 is equal to K prime 1, right? Because they have no they have no acting L here, right? Because the L is equal to 1. Okay, if you see here, because the K1 they're just for the straight one, right? They just consider for the straight one, so they have no L. L is equal to 1, so we can consider that the K1 is equal to K prime 1. So we can get, while calculating for the local, we get directly from the, we can get directly the global one. Okay, okay, and then we calculate as usual for the K by implementing this formula. So we get our matrix for the K1 is, this is for column for Q1, Q2, Q3, Q4, Q5 and Q6. Okay, where you get that is from here. Okay, sorry, you get it from here. Okay, Q1, Q2, Q3, Q4, Q5, Q6, and all of this beam is related to this stiffness matrix. All right, and then same goes to the element 2 and 3, but you need to consider the L here, because you have your L here, right, which is your length. Okay, so from here you get your the local stiffness matrix for Q3 and Q2 is similar, and now when you want to transform it, okay, then you will get, this is K for K2 and this is for your K3. Okay, by representing by Q7, Q8, Q9, 1 2 3, and then let me see either is correct or not. Okay, this is this is element 2 connected between connected to Q7, Q8, Q9, Q1, Q3, Q2 and Q3. So that is mentioned here. Okay, and the same goes to the K3. Okay, so you get your K2, you get your K3. Okay, and then by adding the, and then you make the arrangement with considering the boundary conditions of the nodes for every element. So you can get that Q7, Q8, Q9, Q10, Q11, Q12 is 0. So you can simplify it, and then you will get your global stiffness matrix of your system. So and then from that, when you get your K and then you have your F, right? If you still remember how you get this one, is from this. Okay, you calculated this one, right? This one. So you have your F1, you have your F2, you have your F1, you have your F2, and then you have your F3, and then same goes with others. So you will get this matrix, right? So from that, it's a very straightforward. So in order to find your Q, so you have your K, you have your K, you have your F, so just inverse matrix, and then you will get your Q. right? I think that is very interesting for you to try. The three-dimensional frame will not be covered in this chapter. I think that's all for this topic. If you are not understand or you have a question, you can WhatsApp me directly in 013-6261-363, or you can email me mioikram@ukm.edu.my. Okay. Before we stop, I have one assignment for you. This is e-quiz 1. Okay. It will be covered chapter 4 and chapter 5. This is the individual assignment, so you need to answer all the question, and then please submit this assignment by 17th of June, which is next week, to the UKM folio link provided, and I will open the link after this. Okay, you need to answer 5 questions in total. Okay, I will upload this slide into the UKM folio, and then you can download it and you can answer the questions. So the tips to answer the question is, please don't use a Google search. And then that's all from me, I think. Thank you. I think this is the last topic that I learned, that I teach you guys for this semester. Dr. Rashidi will be covered for the next topic. I think that's all, and thank you so much for your cooperations, and then good luck for your final. Assalamualaikum and jumpa lagi.